So I will talk about EvaxMHC. So it's really one of our core building blocks, and it's used across all of our models. And the reason that it's used across all of our models is that it's really used across the immune system. So it models a very important interaction between the MHC molecule and the peptides. So what I've shown here is a schematic of a cell and a T cell interacting together. So this happens all over the body in the immune system, between normal cells, between immune cells, and between T cells, a central player in the immune system. So what is happening here is that the cell is displaying something via this peptide to a T cell receptor. And this T cell receptor functions kind of like an antibody. So it has similar properties to an antibody. And it recognizes this peptide, and it can recognize a good peptide, something that belongs to the body, and it can recognize a bad peptide, so something that belongs to a disease, a pathogen, or a cancer. So that is really what is being communicated. So the cell could say, I am diseased with a virus, and show this peptide to the immune system, and the immune system will react and maybe kill the cell. Or it could be an immune cell that says, I found this peptide, it is dangerous, we need to do something about it. So that is really why this is so core in the immune system. So the MHC molecule shown here, it's a large protein. It sits on the outside of the cell, and it has this binding groove on the top of the protein, where you have this little peptide located. And what is really crucial here is that this MHC molecule is incredibly diverse. So there are, if we all had the same clone, if we all had identical immune system, you could just have a virus randomly evolve and then say, oh, look, I am no longer being displayed on this MHC molecule, then it would just destroy us all. So that is obviously not very good. So then we have developed this diverse repertoire of MHC molecules that is different from person to person. So that is, of course, nice from an immune point of view, but it's a little bit annoying from a modeling point of view, because that means that we have to model all 26,000 class 1 alleles, which are the class 1 is the one that is sort of communicating I'm in danger from a normal cell to the immune system, and 11,000 class 2 alleles, which is the one that's sort of the between the immune system communication. So we really need to have a handle on all of these. So how we are looking at this problem, we are taking the peptide, which is a string of amino acids, and then we are decoding those down to a letter. There are 20 amino acids, so we use 20 letters for this. The MHC molecule, it's a protein, so it's also composed of amino acids, so we can also decompose that to a string of amino acids. And usually you will compress that a little bit to say that what are the essential amino acids in the binding grooves. And then what is the challenge here is that there is an incredible amount of different peptides that you can have, and there are quite a lot of MHC molecules, so we need to figure out, is a given peptide a binder to a given HLA molecule? And the reason that we need to know this is that if we have a cancer patient that have a certain HLA type, we need to know what neoantigens are being presented by this patient, or we're designing a T-cell vaccine and we need to know which types of T-cell antigens are present in this population. So we need to know exactly what peptides we have to design our vaccine with. And to show here is that modeling this actually has some real-world importance. So Andreas observed, I will mention it again, and Christian will talk about it for real data. But we have actually tried this with our previous version and then our new version, this is designing cancer antigens. So what you see here in the middle is a growth curve for cancer. So what you want is the least amount of cancer possible. So that is the yellow line at the bottom, and that's our new building block here, compared to our older building block, which gives less cancer, but it doesn't quite cure it. So for certain applications, this really does matter that we keep developing these tools. And so the way that we do this is that we, first and foremost, we need the data. So there is luckily a lot of data on this out there in the literature and publicly available. And then we take as much as we can, and then we also generate some of our own. And what we try to do this as cleverly as possible, so it matters the most. And then we look for what are our blind spots in this area. So as I mentioned before, there is sort of a family of these genes. There are many different, and they group together, so which ones are kind of similar. So the ones that are similar, if we already have data for these, we don't need to generate more data, and that is what you see on the right. So we have some on the far left of the plot, which are the ones that we have data for, and these maybe we don't need more data. And then we have some that go to the right. They are far away, and maybe we don't have data. And then we also look at another component, which is how often is it represented in the population. So that means that it is more likely that somebody will have this allele. So then we generate where our biggest blind spots are, and we try to do this continuously. And then finally, for this iteration, we have also upgraded the architecture, the modeling approach quite a lot. So we have used a brand new architecture, a deep learning, and we have also made a new training approach called the generative adversarial network that I'll get back to. So this is how we normally do it. Like I said, we have our MHC molecule on the left encoded as a string of letters. We have our peptide encoded as a string of letters that is 9 amino acids long, because that is the amount of amino acids that usually fit into this groove. And then we feed it into a neural network, which then learns, does this MHC match this peptide? And this works really well, but what we went and saw was that we actually didn't get through all of our data before the model finished training. So we actually had a functional model, but we didn't use all of our data. So that puts us in a nice position, because we can actually upgrade the neural network to something much deeper and much more complicated, because now we are going from a medium data situation to an actual big data situation. So that means that we can make the next generation. And what we do is that we looked at language modeling. So we do that quite a lot when we do proteins, because they are quite similar problems when you put them into the computer. Language is composed of words or letters strung together that makes a sentence that makes sense. And proteins are strung together by amino acids that are put together, and then they sort of make a protein. So very different fields, but the machine learning methods, they are quite similar. And as you all know from ChatGPT and all these things, there has really been some incredible success in this area. So that is also why we are taking a lot of inspiration. And the main source of all of this success comes from, on the left, this transformer architecture. So that is a way of setting up a neural network to learn these language-specific learnings. And what it started with was a machine translation. So you have some input, which could be a sentence in Spanish or English. Then you encode that using a transformer, so the encoder transformer. And that is then transformed into a lot of magic numbers, so a large matrix of just numbers, which is then fed into the decoder, which decodes it into a new language. So that could be Spanish or English or whatever you want. So then you learn the structure of the language. Then on the right is just for showing how ChatGPT works. There you just predict the next word. So you write a sentence, what is the likely next word? And that is actually all that's happening in that model. So that's quite interesting that it works so well. But all of them are based on the transformer. We chose to use the encoder-decoder because it fits our problem quite well. We can encode the MHC sequence, that is sort of the language that we're speaking, so what fits in this groove and what doesn't. And then we use this encoded MHC sequence together with the peptide, and then that is decoded into a prediction. Is this a binder? Is this a non-binder? And this should work really well, but initially it really didn't. It just never ever gave a right answer. It just gave complete nonsense. So that means that we had to take it to the next level to actually train this model to make sense. And the way that we did this is through something called the generative adversarial network, as I mentioned before. So this means that we basically take the network and then we duplicate it. So now we have two networks. So one network, it makes fake peptides. So it basically deep fakes a peptide. And then we have another network that it learns whether or not this the input is a deepfake peptide or a real peptide that we have from our data set. And that means that these models can learn together that it's a more stable way of training them. So initially, you just randomly initialize your model, so that means that the output will be complete garbage. So that means it's really easy to recognize, is it a fake peptide, is it a real peptide? That's a very easy. So you learn slowly, but then as you learn to recognize the difference, the generator, the ones that makes the fake peptides, will also learn to make better fake peptides. So therefore, you train together these models. But that also means that once you are finished with this pre-training step, you have a model that really knows what are the intrinsics of a peptide. So they had a sort of a deep understanding of what is a peptide. So that means that we take it to the actual training and train what is a binder, what is a non-binder. It has a much more stable and improved way of doing it. So we are training together, class 1 and class 2. Normally you train these separately, and then we fine-tune models using only class 1 data and only class 2 data in the end. So what we get is these curves, and they show gradual progression. So you want good recall, that is how often you find your positive, and you want good precision, that is how often is what you say is positive actually positive. So we want to go to the right and we want to go up. So that is so the perfect predictor would be a square in this plot. As you can see, we have our beginning, our starting point framework, and then we add this transformer, and then we get better. And we get better for both. And then we add this generative adversarial network, and then we get better for class 1, and we get a lot better for class 2. So you can really see that the area between the curves is quite large. And that is really significant because it's a much more complicated challenge to predict these class 2 bindings. And we can also prepare. So like I told you before, there are thousands of different alleles. So each dot here is representing one allele. So as you can see, there is quite a difference between the performance of the different alleles. So that depends how much data and so on. But we have really pushed a lot of the alleles up, and we have really the ones that are at the very far bottom. We have also taken those quite a lot up. So compared to ourselves, and also compared to what we have, what you can find in the literature and what you can is freely available on the internet. So like I said before, I'll reiterate, this actually has real-world implications. We can, in our observed model, we can see that the antigens that we design using our newest model, it's much more responsive in the immune system, react to it much higher. If we look at the new antigen immunity, we have a higher precision, so we have more hits when we use our newest model. So that is really why this is used across all of our different models. And finally, the peptide-MHC, it's really key. I would like to of course, reiterate this, and it's really crucial for modern vaccines to get this right. So for some vaccines, T-cell vaccines, the cancer vaccines, you need to get this right. There is no other options. For B-cell vaccines, it really helps. And our newest iteration, version 4 of this building block, it's quite a significant improvement in this field, and that actually improves real-world vaccine performance. So thank you.